Okay, so I thought that I could go over calculating the PI. I have the steps written out. There are 5 steps to calculate the PI. These steps work not only for single amino acids, but multiple amino acids hooked together to form your polypeptide. So as long as you follow these 5 steps and you make sure that you're doing each step correctly, you should be able to calculate your PI. So the steps written out over here, we're going to use an example of a single amino acid and then also go into an example with uh, a peptide to see how it works. The first step is you protonate everything that can get protonated. Then you calculate the net charge. Then you write your pK values from low to high. Then starting from the left, you skip over as many pKs as your net charge. And then you take the average of your 2 closest pKs. So let's see how these steps work when we want to calculate our PI. So over here, I drew the amino acid cysteine, okay? And I'm going to leave the steps over here so that you guys can follow along. So the first thing, and this amino acid is drawn at physiological pH. So the first thing that I'm going to do is step number 1, I'm going to protonate everything that can get protonated. So here I'm going to look at anything that has a negative charge. For example, the carboxyl group at the top, that's going to get protonated. Okay. Carboxyl group at the top is going to get protonated. And then anything that can, and usually like for example, histidine, if that could get protonated, you would protonate that. You shouldn't have any negative charges at the end of the step, and anything that can become positively charged, you should make positively charged. The amino terminus is already positively charged, so we'll leave it as so, and we're good with the first step. Now what we're going to do is we're going to calculate the net charge. So in this case, after I have protonated everything, my net charge is equal to +1, okay? Then what I'm going to do is I'm going to write my pK values from low to high. So I'm going to go 2.0, 8.2, 9.5. Then starting from the left side, all I'm going to do is I'm going to skip over as many pKs as my net charge. So I'm starting on my left, and then I'm always going to end up in between numbers. And in this case, you can think of it like hopping over numbers. So in this case, my net charge is +1. So I'm going to skip over one functional group right over here. And that means that I'm going to end up between the 2 numbers in the middle, right over here. So what I'm going to now do for the last step to get the PI, so the PI is equal to the average of the 2 closest numbers. So my 2 closest numbers in this case are 2.0 and 8.2. 2.0 plus 8.2 over 2 equals 10.2 over 2, which is equal to 5.1. Okay, so all you're doing in this scenario, and this is why it's super, super important to protonate everything correctly, because that'll determine your net charge, is you protonate everything that can get protonated, and because you're skipping over as many pKs as your net charge, you're basically taking off a proton as you go over each net charge. Okay, so I'm going to go through another example so that hopefully this will kind of start making sense. So let's try it one more time, and we're going to do it with this polypeptide. So again, we can do it with single amino acids, we can do it with peptide chains. So okay, over here what we're going to do is we're going to, again, first protonate everything. So let's see, I see a negative charge, that's my first giveaway. I'm going to make this neutral. Okay, I'm going to protonate it. Okay, then, well, my amino terminus, that is already good. This is good right here. My carboxyl group has a negative charge, so I probably have to protonate that one to make it neutral. Okay, alanine, that is also good. So, and then the reason why I gave this specific example is because your positively charged amino acids should also become positive at the end of this step. So what I'm going to do over here is I'm going to make histidine, because at physiological pH, histidine is not positive. We're going to make this positively charged. And now we're good with everything. So I'm done with my first step. Now I'm going to calculate my net charge, and I'm going to see that the net charge is +2. So all I'm going to do is now write my pKs from low to high. So I got 3.5, 3.7, 6.0, 8.5. And again, we always start on the left-hand side, and we skip over as many pKs as my net charge. In this case, my net charge is 2. So I'm going to skip over 2. So in this case, I'm going to go 1, 2. And again, notice I always have to end between 2 numbers. So in this case, I'm between 3.7 and 6.0. So my PI is equal to 3.7 plus 6.0 over 2. And then you can do the math for that. I'm going to, well, it's 9.7 over 2, and I'm not going to do the math, but you get the point. You guys can have different pK values depending on what pK values you're given in your class, but the same idea should work, again, for any amino acid or any peptide. So just make sure that you're following the steps correctly and you're protonating everything correctly, because if you don't, everything else after that falls apart. Now you might, so that's basically how you do it. And I want to also make sure that you guys understand why this trick works, because I think it kind of helps you understand titration curves a little bit better and all that stuff. So over here, I drew, so going back to the cysteine example, I redrew cysteine from our first example from right over here. I redrew it at the bottom, and I also right over here, what I did is I drew out all the different species of cysteine. Okay, so on the left-hand side, we're going from most protonated, and then what we're doing is we're slowly deprotonating it as we go across. So every pKa I skip over, what I'm doing is I'm taking off a proton. So one proton is off over here, then another one over here, okay? And if you go back to your titration curve, there's a video I posted on how to graph your titration curve if you're not sure on that. But the idea I want to emphasize here is that at our half equivalence points, we're plotting our pKa values. So at this first half equivalence point, notice how I plotted this pK value, okay, which is for this carboxyl group. And at that pK value, we said that we have a 1-to-1 ratio of the protonated form and the deprotonated form. So I have a 50-50 mix at where the pH equals to the pK, okay? Now, the idea here is that at the full equivalence point, what I mean, so whenever I get to the full equivalence point, I'm going to only have this species entirely. So at the full equivalence point, you're only going to have one species in your solution, and that's why it's not a good buffer. But the idea here is that every equivalence point or every pKa value that I'm skipping over, so if I'm going from this one, then to this one, what I'm doing is I'm effectively skipping over one pK value, and I'm effectively decreasing the net charge by 1 because I'm taking off a proton. So for example, the net charge all the way on the left was +1. The net charge over here in this molecule is 0. Then it's +1. Then it's no, not +1, sorry. Then it's -1. And then it's -2, okay? So the idea here is that every pK I skip over, I'm gonna basically be taking off a proton, so I'm gonna be decreasing the net charge by 1. So what I'm doing in the trick is I'm protonating everything to get to the most protonated form right over here, okay? Once I get the most protonated form, because I have that net charge, I basically skip over as many pKs as the net charge so that I can get to the molecule where the net charge is 0. So the idea here is that if my net charge was instead of +1, for example, what if it was +2? I would skip over 2 pKas so that I can get to the molecule where the net charge is 0. So the idea here again is just that you're skipping over as many pKs as your net charge so that you can get to that neutral molecule so that you can find your PI. And again, all you're doing once you find that neutral molecule is you're taking the average of those 2 closest pKs to get that true value where that the net charge of those species is going to be 0.